Hello, probably you get the source code because today we are about to discuss source code. So you download the GameMaker Studio and you probably have hard to find how to start it because most of people working with projection and encryptions doesn't use game engines for this purpose, but it is a very good prototyping tool. So you are opening the objects. There is only one object. I don't use object-oriented programming, so I can build a whole game on one object. I have no problem with this. I'm using tables, memory, and so on. And here you have created steps. So this is a setup, this is the loop. There is nothing else. There is a draw, but there is only draw surface that is counted in the loop. So probably you see this code. It should be commented, so the program should start faster. And what it does is pushing some tests. If you go deeper, this is using current function that is in the full-blown version. So here you can uncommented what we are using for informations. However, it is important only what you want to know. So it was used in the development to check some things. And what we're gonna get after this text, if you don't uncomment anything, we're gonna get this report. So we're gonna see how many pieces now it is working, 100 loops. So it will start a bit longer. We are interested only in output, so we're working in output. How many noise error we get, and total nonce. Just by accident we didn't get any. You can put more to test, but we are not interested in this. And so success 45 times, obviously. We found some errors in the given blocks. So in invariant block of 0, errors are not very common. If you see there is 0, 1, 2, 3, 4, 0, 1, 2. This is the start of the quaternion, this is the start of sedonion and octonion. And if you go here, start of the next quaternion and so on. So they are accumulating in the position 7 and 15. So it is like there is no reason to change the invariant here or scramble any operations. You can find it by crypt message version 3. If you go here to single Euclid rotation, left multiplication of sedonion, so you can try to change the invariant, so this position, or change something in sedonion multiplication, like not going from 0 to 7, but different way, splitting the sedonion to two octonions. But in any test that is very simple, which are about to show later on, you will detect where those numbers are aggregating, and the type of the multiplication you are using will be visible just by nonce. If you put 1,000 test, and it is very fast, it means 1,000 blocks, it will be visible what you did to multiplication. So it is not worth of changing multiplication form. It will be plainly visible just by analytics. Yeah, there is no point of abusing it. Paths correct and so on. how many numbers were correct, 0.95. Without nums, 0.95%, 95% of the blocks. Okay, let's quote it. We don't need it. There are two other things that are working very well. These are functions of, if you go down there, Lyapunov test and the cipher test. Those are two working well. Those are no longer in use. They were tests of something. They are no longer in utility, and I was checking a lot of things. So probably this one you have already seen. Parametric testing. It is very slow. It will take long time. It is checking, if we go back to crypt, it is using version 2, the toy version. The version 3 is just made for hardware security module, and it is polished in every possible way. So it is performing this function, and it is performing this in steps here. So here you can unquote a lot of things, like where the nonce are and so on, what round it is. For every round, it will perform rounds only to the point that is the current number of the rounds. And as you see, it is starting from round 1 to round 52, because rounds were set fast previously, and now they are depending on the key. It is derivative of the key, but let's count it as 52 plus around 3, just to have some fun. If you want to know why we want to have this fun, let's unquote this. And this is unquoted, and this is unquoted, and now we can run a test. So how many we put? We put 3 of them. I hope so. It would not be too many. Because we just want to see those numbers. Yep, program started. We don't need a program. Those are statistics, but we don't care about them for now because free test is nothing. Those are those nonce moving in the array. So this is our original key, round 52. This is our key of lower bit, so -1, and this is higher key, +1. So you see there is a lot of not numbers. However, in the last round, our original key returns 0 nonce. It can return 1 or 2, so don't keep with this. At this time we get 0. It is possible to get 1 or 2. However, in the cipher round 51, as you see, it has 1, 2, 3, 4, 10 nonce, so not the numbers. So it is not predictive to tell if there will be nonce or not. As you see, they are quite stable during the runs. However, it is just something almost random. Yeah, it is not random because it is deterministic, but you can tell by those numbers which one is fake. So as you see, those numbers are evolving, and they're going through the collapse a lot of times. So as you see, even original key goes through the collapse during subsequent rounds of encrypting decrypting. This is decryption. So as you see, this is not a data that you can say, oh, not a number, it is wrong key. No. You have to go with pseudonymous multiplication to the last round to know. So it is very expensive for computing. Let's quote it, because we don't need those informations. And we're gonna run a longer test just to see Lyapunov growing and so on. Here is how it is counted. This is our function. This is our loop. And here we are put me stupid. On my computer I cannot put hundreds of tests because I don't have enough RAM. Let's say 90 is something on the edge, because this test is very heavy, RAM heavy, and it not works in loops. It is in the setup, so I was using this when making a program and there were no loop. So let's put it on 80. I will start the test. We're gonna see test numbers. It will hang around 92. When I put 100 it was too much. So yep, let's run and then I cut the video. It started. So 1, 2, 1. Okay, as you see, the program have started. So we don't need our program. We just need to start a setup loop. Delete. We just need this. So this is the test we were run from 0 to 79, so 80 tests. And we have grand summary. The summary is what was interesting for us. So Lyapunov across all rounds was 30, and on the rounds over 30, when it is saturated and stabilized, it is 0.91. You can expect from 0.91 to 0.92. So it is stable. It's starting around 46 and it's going to 0.91. So if you are about to make a random generator about this, it is very aggressively diverges in any this type of functions. I put this function somewhere already in the notes. So this is practically an anti-attractor. Here we have asymptotic growth and Hamming bits. However, Hamming distance in bits doesn't tell you anything because it is not symbolic encryption of the bits. This is a float number. So if you are about to read the float number divergence, you're going here. As you see, with original key, we have divergence. This loss is guaranteed because we are passing information horizon, and if you read the notes, this is the thing. With original key, you don't get the original open text. It is not even possible. So with the other keys that are just 1 bit from it, you are completely lost. So this is gigantic divergence, yeah? Hyperbolic. There is no hill climbing, nothing like this. Pearson, which is not counted here as I see, is around 0 or minus 0.0001. Numeric error. There is no Pearson at all in those datasets. And as you see, this is the bits we are losing. So divergence in the toy version was 2.5%. And it is how I get to this 2%. I know what type of information manipulation I need to do. So how much I have to narrow the bits we are transferring to get the values I expect. Of course, you can go to the error of 0, almost, just by encoding 1 bit for every 64-bit float. But I don't think it is any reasonable choice. So this is possible, but if anybody asks me, yeah, go for 1 bit from floating point number, and then it will work. So this is one test we can use. Let's put it back to 3. Of course, we can put some overflow rules so to see how this was I previously showing those runs are evolving, and the starting ground. We can also put inside some desired key to test. As I remember, no longer. Cut it. But you can use some key you like. Yeah? Instead of random key, you can just put here a key and run this key. So this is one type of test, and the other one is quite wide. I hope it works still, because I was changing the program since I were using toy version. No open text, it will be some random string. Okay, so I'm about to start this test, and this is the last one we are interested in. So this is a very wide test, and it's gonna show a lot of numbers because we are interested in the numbers, in crunching the numbers. So we are at k length, k given, text given. Where is the number of tests? Oh, it is set automatically. So you have to manipulate how long time it should take, and it will calculate something and guess how much we want. Okay, so let's go for it. There is a lot of things we need to. Okay, our program started, so we are closing the program. And we are back here. Those informations are part of test I'm not interested in. We are going up here to ground report somewhere. This is our probing. So if you want to make a broader test, you change some values here, like this one, and then you can run more tests. I just put it some reasonable range, so you don't wait hours to it. Usually I started it at night to see. So what we have in the ground summary? We have completed 10,293 probes, so blocks. How many blocks and so on. Around. We have found 70,183 not numbers per probe and so on. So we were testing to decipher a message with a random key. Here we have a correlation. Have a fun trying to attack it analytically. This is just a rounding error. As you see, chi-square is very interesting. Residual, yeah. This is the statistics of the nonce. However, if you see how they're built, you see discrepancies here. They are very small, but the difference is enough to tell how the multiplication works. So this is cleaned residuals. So if you have here some zeros, it's a real number we have beneath to some degree. And we have performances. And I was trying to find the potential keys using this. So this is why this function returns all the potential keys, a lot of them. Like this way, I found there existing lot of minimas, which are false. They exist somewhere in the regions. And it was for 32-bit message passed. So I tried to use it and average the send bits to the level where decoding will almost every time give some reasonable numbers. So not a lot of nonce, but something that looks like a message. So false key gives something that looks like a message, which it isn't, which we checked previously in other films that were about testing loops, how they differ. But this is the part of development process that I was checking how to exact set the numbers to get it viable. So not only it is right or wrong decryption, but also how to make it tricky to tell if it is wrong decryption. And so it was the part of the development process. So if you want to test how those functions work, you go here, you put some numbers and you go with the function. It is very hard for me to explain what I did month or 2 months ago, so it can sound quite weird, but that's how this program works, and yeah, I'm not good for explaining. I'm about write math and code. So yeah, have a fun with this. Thank you.